Hello everyone, my name is Yedi Zhang. I'm from Shanghai Tech University. Today I will present our paper, QVIP, an integer linear programming-based formal verification approach for quantized neural networks. This is joint work together with Zhe Zhao, Guangke Chen, Fu Song, Ming Zhang, Taolue Chen, and Jun Sun. We all know that building a reliable AI system is very difficult but necessary, especially when it is used in some safety-critical systems. Here is a picture of a wet truck that was processed by a neural network but classified as cloud. It is conceivable that such a network will pose a safety hazard once deployed in an autonomous driving system. The goal of verification is to provide rigorous and provable guarantees of network's behavior, or to say, to mathematically checking that the network's behavior satisfies a given property. Literally, there are many properties to describe the behavior. In this work, we focus on the robustness property, or more specifically, qualitative robustness. Given a neural network and an input region, the network is robust if and only if every sample in the region is classified into the same class. So far, there has been a significant amount of work focused on the verification of robustness. Here we list the second international competition of the neural networks verification, and all of these studies focus on real-valued neural networks. That is, the parameters and activations are both real-valued numbers. In fact, the parameters in the modern networks are typically stored as floating-point values, and for some resource-constrained devices, they can be quantized to even lower bitwise. For example, Tesla's autopilot system uses an 8-bit quantized neural network. However, it has been shown that robustness and vulnerabilities to attacks do not always transfer between real-valued and quantized neural networks. So, specialized verification techniques are required for the quantized neural networks. Compared to the real-valued networks, the verification of quantized neural network, that is QNN, has not been thoroughly investigated yet. The existing techniques for verifying QNN leverage Boolean satisfiability, SAT for short, or satisfiability modulo theory solving, SMT for short, or binary decision diagrams. As we can see, most of them are designed for 1-bit quantized neural network. And for the multiple-bit quantized neural network, the existing techniques are all based on SMT solving, which are sound and complete, but have fairly limited scalability. In this work, we first introduce a novel verification approach for n-bit quantized neural network, which reduces the verification problem into a pure integer linear programming problem. It preserves the original semantics of QNN and utilizes interval analysis to improve the verification efficiency. Then we propose a framework to check the qualitative robustness and compute the maximal robustness radius based on that. Finally, we develop a tool and conduct thorough experiments to show that our method is significantly faster than the SOTA. We first introduce the concept of quantization. A quantization configuration is a tuple where tau indicates if the quantization is signed or unsigned. Q gives the total quantization bit size of the number, and F gives the bit size of its fractional part. So we say a quantization configuration defines the quantization grid limits. Then, given a quantization configuration, the quantized number hat U of a real-valued number U is defined as follows. We first multiply U by 2 to the power of F. Then we round it into its nearest integer, and finally clamp it within the grid limits. For example, the real-valued number 1.23 will be quantized into the integer 5 with respect to the quantization configuration assigned for 2. Now, given a DNN, assume that the quantization configurations for the input, weights, bases, and outputs for each non-input layers are also given. First, we can get the quantized input, quantized weights, and quantized bases for the QN as follows. Then, we can get the quantized neural networks by rewriting the activation functions as follows, where ReLU functions in real-value DNN are replaced by a rounded clamping function. Note that The factors here are used to align the precision between the input and output of each layer. Here we have an example of DN and its integer counterpart under the given quantization configurations. As we can see, in this QN, the inputs and all the parameters are quantized into integer and the activation functions are replaced by a rounded clamping function. The main idea of this work is to reduce the verification problem into a pure integer linear programming problem with no objective functions. Then we use the solver Groby to solve this ILP task. So the key point of this work is how to encode the input regions, the properties, and activation functions of QNs into integer linear constraints. We first give an overview on input region and property encoding. For the input region, here we show the ILP encoding of input region defined by L infinity norm, which limits the maximal perturbation for each element in the input vector. The encoding is quite intuitive. For the properties, currently we'll focus on the robustness property of QN. Note that any properties that can be expressed by integer linear constraint could be verified by our approach. Recall that a quantized neural network is robust within an input region if all the input symbols have the same output. So for a classification task, it suffices to check if there exists an input such that the argmax y differs from the predicted class G. If so, then we can say we successfully find a counterexample and the robustness property does not hold. Otherwise, the network is robust for the given input region. To encode the constraint, argmax y is not equal to G. We introduce a Boolean variable v for each output class I such that the output hat yi is no less than or larger than hat yg, if and only if the Boolean variable is true. Then, the non-robust property can be encoded by such a single constraint, that is, the sum of all the Boolean variables should be larger than 0. And these constraints can be further encoded by these sets of linear constraints with big M formulations. Now we come to the encoding of activation functions. The idea is that we first transform the activation functions into piecewise constant functions, which can be further expressed as sets of integer linear constraints. We will first show how to express a piecewise constant functions as a linear constraint set. Let's consider such a piecewise constant function with input x defined between a0 and ak. In fact, we can always use the following 4 integer constraints to encode it, where x and y denote the input and output of the piecewise function. v1 to vk are all Boolean variables. Intuitively, the first constraint ensures that the input x falls in one and only one interval. The second constraint reformulates that the output 1 equal to fx. And the last 2 constraints ensure that the upper bound and lower bound of intervals respectively. Note that the number of variables we use here is decided by the interval value of x. Then we transform each activation functions into a piecewise constant function. In fact, we found that by replacing the linear parts with a real-valued variable z, the activation functions in QN is indeed a piecewise constant function of z with upper bound and lower bound given by the grid limits. Then we can get such a piecewise constant function. Note that the positive and negative 0.5 here are added to encode the rounding functions, and the t1 to tk are all the integer values that can be taken within the grid limits. Now we finish all the encoding parts and get a set of integer linear constraints, which can be further solved by Groby. Recall that the number of variables we use here is decided by the input interval of piecewise functions. So intuitively, one way to improve the verification efficiency is to tighten this interval boundary. In this work, we use interval analysis to get tighter intervals for each neuron. For the evaluation, we train 4 architectures under 2 datasets, MNIST and Fashion MNIST, with different quantization levels. As we can see, all of these networks have high accuracy. Hereafter, we denote by PXY the QNN using the architecture PX and quantization bit set Q equals to Y. And for each verification tasks, we set the time limits as 2 hours. This picture demonstrates the effectiveness of interval analysis where the input regions are given with attack radius from 1 to 30. The blue bars in the above figure give the proportion of all the accelerated tasks, and the yellow and red ones give the accelerated tasks for which the verification results are non-robust and robust respectively. The first row in the below table shows the reduction rate of the number of Boolean variables used during encoding with interval analysis. The other 2 rows give the average verification time in seconds with and without the interval analysis. Overall, we can observe that the interval analysis can significantly reduce the number of Boolean variables and the product terms in the integer linear constraints, and hence reduce the verification cost. For the robustness verification, we compare our tool with the SOTA SMT-based verifier using networks of varied architectures. The attack radius here is from 1 to 4, and it defines input regions of different sizes. The first columns give the total number of verification tasks for each attack radius and each quantized neural network. Columns SR show the success rate of verification, and columns time give the sum of verification time in seconds of all the solved tasks. Note that we also show the sum of verification time of QVIP for solving the verification tasks that are successfully solved by the SMT-based method, which are given in the parentheses. We can observe that our tool QVIP solved significantly more verification tasks than the SMT-based method within the same time limits in both the single and multiple thread mode. We next conduct scalability evaluation experiments on other quantization levels and larger attack radius. The results show that our tool scales to larger networks with the attack radius R up to 30. We also observe that the verification cost is non-monotonic with respect to the attack radius. To understand the reason, we further analyze the distribution of robust symbols and non-robust symbols solved by our tool. To understand why the verification cost and the attack radius are monotonically independent, we further analyze the distribution of robust symbols and non-robust symbols solved by our tool. The blue and yellow bars show the proportion of robust and non-robust symbols among all the solved tasks, so the red dotted line reflects the change in the verification success rate. We found that the robustness of quantized neural networks with respect to input regions with smaller or larger attack radius is relatively easier to prove or falsify, while it is harder for the attack radius close to the robustness boundary. We also found that although the accuracy of these networks are similar, their robustness are quite different, and particularly using more quantization bits results in an overall more robust quantized neural network, that is, more robust symbols under the same attack radius. Finally, we evaluate our methods on the application of the maximal robustness radius computation. Here we use 2 networks under different quantization levels and run 100 computation tasks for each. The computation here is based on a binary search, that is, search a potential radius R in a binary manner, and then check whether the network is robust or not. As we can see from the scatter plot, a higher bit quantization level usually results in an overall more robust quantized neural network. So to conclude, we introduce QVIP, a novel integer linear programming-based verification approach for n-bit quantized neural networks, and implement the approach into a tool and conduct thorough experiments. The experiments show Our approach is much more efficient and scalable than the existing SMT-based method. And from the experiments, we also find that the quantized neural network is overall more robust if quantized with more bits. Our verification approach is sound and complete. Thanks for your attention.